Okay, in this video I'm going to show you how to solve higher order differential equation. As we know that complete solution is equals to the sum of complementary function and particular integral. So let's say I have a question: d squared y plus 4y is equals to e to the power 2x plus cos 2x plus 1 plus x squared plus 9. So here d is an operation of integration which is equals to d by dx, or you can say it is a derivative. So uh, first of all, to solve this equation we need to find out the complementary function of this equation. So for finding the complementary function, the right hand side of the given equation will be replaced by 0. So the remaining auxiliary equation will become lambda square y plus 4y is equals to 0 by taking y common. So my remaining auxiliary equation will become lambda square plus 4 is equals to 0. So the roots of the given equation will be plus minus 2 iota. As these roots are complex, so case number 3 for complementary function will be used. So my complementary function will be equal to c1 cos 2x plus c2 sin 2x. For finding the particular integrals, this is quite challenging part of the equation. My particular integral is equals to 1 upon function of d into function of x. So applying the rule number 1 for e to the power 2x, my rule number 1 says particular integral is equals to 1 upon function of d by e to the power ax. A is an arbitrary constant. So we have in rule number 1 we have to replace a function d by a. So let's replace function d by a. A is equals to 2 in this situation. So my particular integral for rule number 1 will become 1 upon 8 e to the power 2x. Now let's solve for cos 2x plus 1, which is rule number 2. The particular integral for this situation will become 1 upon function of d cos ax plus b. These both are arbitrary constants. So my function d is d squared plus 4. Now in this situation I have to replace d squared by a minus a square. Let's replace it. So the equation will become y particular integral is equals to 1 upon 0 cos 2x plus 1. Now, so my solution goes to infinity, so it is not possible. So I have to take first derivative of function d. The first derivative of my function d will become 2d. So the particular integral equation will become yp2 is equals to 1 upon 2d cos 2x plus 1. Now I have to multiply and divide by d so that I get the d square in the denominator. By multiplying and divide by d, I get d square in the denominator. Now I just have to replace d square by minus a square. So my equation will become minus d square upon 8 cos 2x plus 1. As we discussed earlier, the operation of differential is equal to the derivative, which is d by dx, so the derivative of cos 2x will become minus sine 2x plus 1, and the derivative of this function is equals to 2. So my particular integral for rule number 2 will become sine 2x plus 1 upon 4. Now my last part of the equation is left only, which is a polynomial equation. So applying rule number 3 for this polynomial equation. In this equation, I have to take a common out of the lowest degree term in the function d. So lowest degree term is 4. I take 4 common out, so it will become 1 plus d squared upon 4. Now I will take this thing to the numerator, so it carries a whole power negative 1. As we know that according to the binomial theorem, 1 plus x whole power negative 1 is equals to 1 minus x plus x squared plus x cubed minus x4, and so on and so forth. So let's apply binomial theorem over here. My particular integral for rule number 3 is equals to 1 upon 4, 1 minus d square x square plus x cube, 1 minus x plus x square minus x cube, and so on and so forth, multiplied by this. So this equation will become 1 upon 4, 1 minus d square upon 4 plus d 4 upon 16 minus d 6 upon 64. As we know that this operation of differential is equals to the derivative dy by dx. So the derivative of this equation is 2x, and the double derivative of this equation is 2, and the triple derivative of this equation is 0. So we don't have a triple derivative of this equation. So d by d4 by d so d the fourth derivative of this equation will become 0, so the higher derivative will also become 0. So let's multiply this equation by 1 and this, so we get x squared plus 1 minus d squared upon 4 x squared plus 9. So the double derivative of this equation will become 2. So let's rearrange this equation. By rearranging this equation, I get 1 upon 4 x squared plus 9 minus 1 upon 2 x. So my particular integral for rule number 3 will become 1 upon 4 x squared plus 17 upon 2. Now let's put all the things together in this form, the complete solution. So by putting this, I get my complementary function, my particular integrals all over here, as we discussed earlier, my complete solution of higher order differential equation is equal to the sum of complementary function plus particular integrals. Thank you for listening.